Welcome to Digital Electronics Lecture 11 Part 2.
Okay, so this is our first example. So we'll write the VHDL code for D flip-flop. Let me use the laser pointer. Okay, so we need to design the D flip-flop using the VHDL. This is the typical block diagram of D flip-flop. So usually in D flip-flop you have input. This is your D, and this is your clock. So whenever your clock is activated, so your data will be transferred to that Q, and Qn is your inverse of Q, right? So this is your truth table itself given. So if you look at here, when your clock is 0, then it's not doing any function actually, storing the value or whatever value you have previously to store the values. It doesn't really matter what your D is. Again, if your clock is 1, same thing, storing the values. But if your clock is activated, which means either it is positive edge or negative edge, then your data will be transferred. Okay, so your clock is activated, so you have D, so whatever value you have as the input, it will go to the output in Q. So 0, here 0, and Qn is inverse of 0, Q. And you have 1, so it's going to the output as 1, and if inversion is 0. Okay? So it's updating the values. So this is the basic concept of D flip-flop. So you need to write a VHDL code for that. And we have here the 3-part library function, entity, and architecture. So just one thing you need to remember here, like in architecture, we have actually two functions. One is synchronous function, and another is asynchronous function, or synchronous action, asynchronous action. So whenever we are writing the VHDL code, so first we will check for the asynchronous action if there is an asynchronous action. Here is no asynchronous action. Asynchronous means like if you have reset or preset, something like that. Then we need to check for that one. Like here, after begin, we check if reset is 0, then do something. Okay, if reset is 0, do something. Later on, we'll check for asynchronous action. Synchronous means with clock. So with clock is transferring the values. So if clock is active, then transferring the values D2 or something like that. So remember that. So it will be needed for the other example as well. Okay, so we started with the library function, and in the next letter I'll describe the other things. So next part is your entity part. So in the entity we declared the input and output. We have D and clock as the input. So in port we declared D and clock as input with single bit, and Q and Qn as output. So Q and Qn output. So remember here the semicolon is after the first bracket. So you start here, first bracket, and end here, and after the semicolon. For all other cases, semicolon is after standard underscore logic. So this is your entity part, end of entity, and within architecture, so give the name whatever you like, and after begin, so you give the name of process as well, and here the process is sensitive to your clock, so you write the clock. Sometimes it could be sensitive to reset as well, so you will put the reset, but here it is clock. So again the begin, so it is activated only when your clock is high, so you can write if clock event and clock equals 1, or you can write if rising edge clock, then so your q will be getting the value of D when your clock is activated, right? And Qn will be getting the value of not D, because this is inverted of Qn. And end if end process and end architecture, which is very typical setup for D flip-flop, and if you run it, then you get the expected output for D flip-flop. Okay, so now I'll show you how it looks like in the software. So let me use the laser pointer again. Okay, so this is your IC project navigator, the software we'll be using. So here are a couple of uh, examples I have tested, and this is the example what I discussed already. So you can look at the code here. So library function is declared initially on the entity. So within the entity we usually have the D and clock as an input and Q and Qn as an output. All of them are single bit. That's the we use the standard underscore logic as we discussed. End of entity. And architecture, I just gave the name. I use the behavioral. You can use as required. And after begin, I gave the name of the process, and our process is sensitive to clock. I wrote it. And after begin, so if rising underscore h clock, then your Q, the output Q will get the value of G, the input data, and Qn will get the value of not D, the inverted of D or inverted of Q. And I started if, so end if, I started the process here. So this process, so end process, and I started the architecture, end architecture. So if we run it, then it will give you the expected output. Thank you.
So this is how it looks like after writing the code if you synthesize it. So basically if you click here synthesize, double click, then it will go tick, and here translate tick and generate tick. So after that it will show something like that. Okay, so if your code is okay, then it will synthesize something like that, the schematic. So the schematic, you can check it with your code whether it is expected schematic or not. So here is an assignment. You need to write the VHDL code for JK, SR and T flip-flop.
Welcome to Digital System Design lecture series. So in this question, so it says write the VHDL required for 3-bit counter module that counts 1 to 6 as required for the LED die laboratory. Draw the complete state diagram for the circuit design. Okay, so the thing is you need to design a counter which will count 1 to 6. The question already says it's a 3-bit counter, right? So 2 to the power 3 means 8. So there will be 8 combination, but as it suggests you need to count 1 to 6. So you can go up to 6. Okay, so let's look at the architecture first actually for the counter. So it will obviously activate on clock. So this is a synchronous action. That means whenever we have the clock, then it will activate it. So let me use the laser pointer. So if you look at here, so for synchronous action we can check it using this statement, like if rising edge clock, then if our counter is 1106, then count equals 01. So if it goes to 6, then our count will be 01, else our count will be count plus 001. End if and end if, we are closing the end, right? So what does this doing, right? So initially we have say counter value 001, and we are adding 1 all the time. So say like this is your initial counter value count within that count register, and you're adding 001, and later on again 001. So 1 on 2, 2 on 3, 3 on 4, something like this. So it goes up to 6. Whenever it reaches 6, then you're setting it to 1, because it says 1 to 6, so that's why. So we're setting it to 1. So initial value is 1. So we can see we need a counter register, right, to keep the track of the previous values, and adding with 1 we need another counter register for the updated value. So just look at here, so both of them are named as count, right? So if you think about a black box, so that's within that black box. So we need to declare them using the signal. So that's why you call it signal count. Then standard logic vector. This is the shortcut SLV. As this is 3-bit counter, so 3 down to 0. Okay, just look at here. Okay. Say by any chance, if you do the reset, or somehow it goes all of the 3 bits high, so what you can do? So you need to go to that safe state, right? This is your unsafe state, you can say so. Or this is your disaster, this is undesired state. So we need to change it here. So if it reaches say 6, we says equals 6. So if it's more than 6, then what will happen? So that's why we put count greater than equal. So if it is 6 or greater than 6, that means this is addressing this one 7, then we are setting it to 001. So there is no way to go to this undesired state, right, for this setup. Okay, and other things are uh, same as it is what we used in the last slide. Okay, so now this is the typical VHDL module. So we'll try to write the VHDL module for the question. So first we will start with the entity and then the architecture. Okay. Okay. So this is the uh, block diagram of our counter. So we have a counter, and top level we have roll button, we have clock, and this is our output count, right? Okay. So whenever our clock is active, then with the press of roll button, it starts counting, right? So in the port, we're declaring the roll button and clock as the input. This clock is not shown here. You can show clock as well as the input, and count is our output. Just remember, this count is 3-bit vector because it says 3-bit counter, so 2 down to 0, 3-bit. And within the architecture, we use the signal as well. So just look at here. We have the counter. So this is one kind of register, the counter. So we need to remember the previous values, and we need to add 1 with the previous values, and then we get the updated values, right? To keep the track of the previous values and know the updated value, we need some sort of register with this counter here. So this is within this top level. This is kind of internal things. So that's why you call it as a signal. So you put the signal, which name is counter, and this is also 3 bit, as a counter is 3 bit. Okay. So after begin, so we need to connect that counter with the output port, right? So output port we have count. So we need to have the connection. So count equals counter. So this is providing the connection. Otherwise, you will not get the updated values in the output port. Okay, so next the process, and within the process we have the sensitivity list. So our counter is sensitive to the clock. If we have any other asynchronous input, then it may be sensitive to that asynchronous input as well. But right now our counter is synchronous, as it's keep updating with the clock values, right? This rising edge of clock value. So then the begin and starting the synchronous section. If we have asynchronous section, we will start the asynchronous, check the asynchronous section first, later on synchronous. Okay, so for the synchronous section, we have if rising edge clock, then. So we are saying if our counter greater than equal 6, as we discussed in the earlier slide, and then our counter will be 001. Else our counter will be counter plus 001. So we start ending the if, ending this if, and end process. But look at here, we didn't incorporated the roll button. So our roll button, this is also synchronous. So that's why we need to put it within the clock. So we need to have another if statement where it will be checking for roll button. Like if our roll button is 1, then if our counter is greater than or equal 6, then it will be 1, something like that. Right? So in the next class, we will look at the updated module. Okay.
So this is the summary of the code what we already discussed. So you have the library portion, you have the entity portion, and you have the main architecture portion. So you can write it all together and you can try it in the software as well, whether it is running or not.